welcome back to learning how to tune PIDs. Today we will be talking about the arm mechanism. So as you can see, I already have the arm mechanism set up over here, and I have the position and velocity set up here. I've also set up the live tuning for the arm mechanism. If you need help setting any of that up, please go back and watch the other tutorials that I've made for the setup process. And then also the first couple minutes of the elevator for some of the setup stuff if needed. But I'm going to jump right into tuning. So the first thing we need to do is, as we did with the elevator, if you watch that video, is to set the kg value. So I'm going to be setting the set point to 8, because if you see this little red line here, that red line is the max position, the soft limit of the arm. And so if I set it to 10, then it kind of glitches out. That's just a thing with the simulation. It's not something that's probably going to happen on your robot, or I hope to God it doesn't happen. And so that's just something that I'm doing. You can set it to whatever position you found on your robot. If you need to, you can move your your arm, and find a position that works well for you. So now that we've set up the position, we can now start tuning kg. So as I did before, we're watching for this position. Oh, let me zoom in. We're watching this position, this blue line, to see if it goes up at all. So we're going to go 0.2, nothing, 0.4, nothing, 0.8. Oh, we saw something. So now I'm going to set it back to negative, so it comes straight back down. And then I'm going to set it between 0.4 and 0.8. So 0.6, 0.6, I don't see anything. So now we can go to 0.7. 0.7, I don't see anything. 0.75. 0.75, I don't see anything. Let's make sure that, yeah, live tuning is still enabled. 0.8 still does stuff, so we want to go negative. So 0.75 was good. And then now we're kind of closing in on between 0.75 and 0.8. And so now I'm just going to kind of increment a little bit. So 0.76, nothing. 0.77, nothing. 0.78, nothing. 0.79, oh, we see some movement. So 0.78 is good. Now, because this mechanism is a little bit more finicky, I want to get kg down to like 2 or 3 decimal places. So now I'm going to try 0.785, and that's moving. So we want to go less than 0.785, so 0.782. And you can see that that is not moving. This might look like it's moving, but that can also be because of some steady state errors. Actually, you can see at 7.81, this is not moving at all. So we want it to be a little bit between 0.781 and 0.782. So that way this line is not moving at all. So now we can try 0.7815, and that's fine. So maybe 0.7187. And oh no, there's some wiggles there. So I'm going to keep it at 0.7815. You can see this line is pretty much flat. This position isn't changing like at all. And so for these more finicky mechanisms where the gear ratio is a little bit lower and these values mean something different, then in the elevator, making sure that you have a pretty accurate to 3 or 4 decimal place kg value is pretty important. Now, what we're going to do is we're going to start tuning our P value. So now I'm going to go 0.1. That's really slow, as you can see. So I'm going to go to 0.2, still pretty slow. 0.4, still pretty slow. 0.8, still pretty slow. 1.6, still pretty slow. And now that's reached the position. I'm going to go back down, and that's, as you can see, pretty slow. So we're going to go up a little bit higher. And this is something that you need to kind of do by feel. This mechanism is pretty heavy, and it's a big arm, so it has a lot of inertia, which means it doesn't want to move a lot. So a lot of the times, like in this example here, our thing is moving pretty slowly, but if I pause, why won't it let me? Sorry about that. if I pause and I look at this graph, you can see it kind of dips down underneath the position. And so what that is, that is called overshoot. And so we want to minimize overshoot because, for example, if this arm has a hard stop, if we set it to a position, we want it to go exactly to that position. We don't want it to ram into the hard stop. And that's what this little dip shows. It indicates that we're gonna hit that hard stop if the hard stop is at that point. And so we don't want that to happen. And so one way where we can do that is by just decreasing the p-value, but in this case, I'm going to be showing kind of how to do it with, actually, I will be showing, sorry about that. I'll be showing you how to do that with just the kp value. So what we want to do is go back to the present. You know it's in the present if you keep scrolling and then you see these numbers are moving on their own. And we're going to decrease it. So we're going to go, because I can't do the math in my head, I'm just going to go, we were at 1.6, 3.2 is too high, let's go like 3. And so now, let's look at this curve. If we zoom out, we can still see that it's overshooting a little bit, but honestly, it didn't change much. So I'm just going to bring it back to 3.2, and we're going to change how this is using motion profiling. So if you go into the code and you go into the ARM subsystem, you can see that there's these closed loop controllers. And so these are the max velocity and max acceleration for our arm, and they're in degrees per second and degrees per second per second. So some of this is intuition, some of it is trial and error, but you usually want your max acceleration to be higher than your max velocity, because in most cases, not all cases, most cases you want your mechanism to accelerate to its max velocity in less than a second. And if your acceleration is lower than your velocity, then it'll take more than a second to accelerate to your final position. So I want this arm to move at a maximum velocity of, let's see, of about, this is in degrees per second, I believe. And so, sorry, this is actually in a different unit than what you would expect. And so I'm just going to go based off of what I can see here. So from a position like 8, so if I go to 8 and I want to go from 8 to like -10, that is around about 60 degrees. So I want to be able to go to there in less than a second. So including acceleration and stuff, I probably want my maximum velocity to be about 90. So now you can see that if I don't have this maximum velocity and I did that, you can see that actually, if I go to like 15, it's a lot more obvious. So if I go here, you can see how much slower it is than before. So if I go from like -10 to 8, it's only going up a little bit. But if I set this back to like 90 and I go to -8, you can see the maximum, this line is slightly shallower than this line. And so that's what motion profiling allows you to do. It's less obvious in this case, but for example, we can try setting our velocity to something like 45. And as you can see here, it made our motion a lot smoother. If I go again, you can see that it doesn't change as nearly as fast as it was before. If I set this back to 0, which means that it's default, you can see that it's like immediately jumping to this velocity. And this can be an issue whenever your motor is running, because this is not how a motor works. So you need a little bit of time to ramp up the motor rate, which is why sometimes using exponential profiles is better, or usually using exponential profiles is better. But in this case, we're doing trapezoidal just because it's a little bit more intuitive. But that's a discussion for another time. Here you can see that the max acceleration impacts a lot how fast our mechanism moves. So if I go now, it still has this little hiccup. And so, but if I decrease this maximum acceleration to a low value, then you can see this jump is a lot less noticeable. So here's a jump before, here's an after. It's less noticeable than it was before. Um, uh, so now I'm just decreasing this value a little bit just because, as you saw there's still a little bit of a jump, and so I think that might be because of the KP value. And so now we can look at this, and now we can see that there's virtually no overshoot. That's a technical term. It's not really, there's no overshoot now. And so now we can kind of play with this value, try to figure out what would be what's gonna not make it overshoot. This, from what I can tell, looks pretty solid, although there is a little bit of a jump there, so we're gonna decrease it a little bit. And now you can see it's pretty smooth. And so now that we've gotten most of the way there with just PID tuning, we can start increasing some of these motion profiling constraints so that we can we can have smoother movement whenever we go to our positions. And so this right here from this time frame right here is a pretty good example of what we want to see. Obviously, it's not perfect, but you can see how it's pretty boxy in shape. It looks pretty rectangular. Obviously, we're not going to get exactly what we want, but that's kind of I guess you could call it a trapezoid. It doesn't really look like a trapezoid to me, but that's kind of the motion we're looking for. We're looking for, it's less of a trapezoid, more of a rectangle. Whenever we go, this is our one set point, this is our second one. We want it to look like this. We don't want it, if I scroll back in the timeline, we don't want it to look like this, where it's kind of like all over the place. Because that is less accurate, and we're gonna see it's gonna take longer and it's gonna be less efficient than it was before. So sorry for some of the rambling that I did. Generally, what we're doing is we're tuning kg to a pretty precise value, then we're going to be using kp to a pretty nice value, and then we are going to use our motion profiling constraints to prevent overshoot, prevent undershoot, prevent the mechanism from breaking in any way that might prevent the mechanism from being too free or too energetic or too extreme in its movement. And for example, I would break a lot of chains during the crescendo season because of no motion profiling. So motion profiling helps smoothen out a lot of that kind of jerkiness that you might otherwise see in a mechanism. And these same skills and these same theory apply to whenever you're tuning with, for example, Phoenix Tuner or Rev Hardware client. And so even if it doesn't look the exact same as it does here, you still can apply the techniques, you can still apply the principles that you've learned here whenever you're doing your own tuning. So I hope this video helped you, and I hope to catch you in the next one. See you.